Hi everybody, welcome to another video in course Algebra, section 3.4, zeros of polynomials. First, the rational zero theorem. If we have a polynomial that has integer coefficients and p over q is a rational zero of f of x, then p is a factor of a naught, which is the constant, and q is the factor of a sub n, which is the leading coefficient. So another way to put it, possible rational zero, we take this form. So the key here is it's only possible, so that may or may not be the case. And the solution is going to be rational solution. Only irrational solution will not be covered in this theorem, and imaginary solution, irrational solution will not be in this theorem. So if it is a rational zero, then it will be in this form: factor of the constant term over the factor of the leading coefficient. Right. So again, it's only possible, so may or may not be true. I mean, it may or may not be a zero of the polynomial. So this possible here means it may or may not be actual zeros of the polynomial function. You see that in a bunch of examples we have in this section. Right. So just jump right into the first example. List all the possible rational zero for this polynomial. So the constant term is 6, and the leading coefficient, that's just x cubed, so the leading coefficient is 1. So according to our theorem, we have possible rational zero would be factors, would be, if it is a rational solution, it will be in the form of the factors of the constant term over factors of the leading coefficient. Now, factor of 6, 1 going to 6, 2 going to 6, 3 going to 6, and 6. Those are the number that are factors of 6. Factors of 1 just be plus or minus 1. Now, if we divide by 1 will be itself. So in this case, we only have 1 divided by 1, 2 divided by 1, 3 divided by 1, 6 divided by 1. So the possible rational zero will be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So if the solution is rational, it must be one of this. So as you see, if the leading coefficient is 1, then we only have integers, possible integers, as a rational solution. Like I said, imaginary and irrational solution, of course, does not include it in this, obviously. Right. Now as you see, there are like 8 solutions here. I mean, if there are solutions, there should be 8. But the qubit equation, there should be at most 3 solutions. So not all of these are 0. But if they are 0, they have to be, if they are rational 0, they have to be one of those forms, one of those numbers. Right. So again, the possible meaning that if the zeros are rational numbers, they must be in this set of numbers. Right, let's look at another example. List all the possible rational zeros for this. Once again, just say the possible rational zero be equal to the factors of the constant, factor of -6 over the factor of leading coefficient. Right, now, factor of 6, 1, 2, 3, and 6. Factor of 4, 1, 2, and 4. Right, now, once again, if the zeros are rational number, they must be in this form. Right, so in this form, what do we have? We can write 1 over 1, 2 over 1, 3 over 1, and 3 over 1, 6 over 1. So at first we will write, if we divide all of this by 1, we have plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are the possible. If we take every number on the top divided by 1. Now if we take all the numbers on the top divided by 2, then we have 1 over 2, 2 over 2, 3 over 2, and 6 over 2, right? 1 over 2, 2 over 2, 3 over 2, and 6 over 2. However, 2 over 2 is 1, we already have that. 6 over 2 is 3, we already have that. So just 1/2 and 3/2 here. Plus or minus 1/2, plus or minus 3/2. Right? And now we divide by 4. So 1 over 4 plus or minus 1 over 4 plus or minus 2 over 4 plus or minus 3 over 4 and plus or minus 6 over 4. Right? Now, 1/4 is new in this list. 2 over 4 is 1/2. We already have that. 3 over 4, well, that's new. 6 over 4 is 3/2. We already have it. So what's left is the list for the possible rational zeros, because there will be a lot of them. That means not all of them are actual zeros. Right. So once again, plus or minus 3, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/2, plus or minus 3/2, plus or minus 1/4, and plus or minus 3/4. If the zeros are rational numbers, it must be one of those numbers. Right. Now, so that is very important to help us to find zeros of a polynomial function. Right. Look at this zero. We actually find all the zero for that problem. So this line the long problem. So try to save space. Just cut the page in half here. Right. Now find all the zero. So the first step here, we have to start at some point. And if we know 1, 0, we can reduce the problem to something, to quadratic equation. You will see. So first, I'll do the same thing. Find the possible rational zero. I'll take the factor of the last one divided by the factor of the first, factor of the constant. -3 over factors of the leading coefficient 1. So factor of 3, 1, or 3, and factors of 1. So we have 1 over 1, 3 over 1, So those are the possible zeros. Now, next, we're just going to test which one of them is. So check for actual 0. Right. We just pretty much test. So we put 1 into the function. Right. Of course, one way to do that is if you enter the function into the calculator. So if we have a calculator, it will simplify a lot. But in this section, I'll do both with and without the calculator. So in that case, we go to the table and we see that when x equal to -3, y is equal to 0. So -3 is 0, -1 is not, 1 is not, and 3 is not. Right. Now, right. Of course, if you want to evaluate the values of function as something else, hit variables, y variable and function y1. In that case, we can evaluate at anything. For example, that gives us 0. Right. So that's nice if we have a calculator. If we don't, we just evaluate this by hand. And a nice way to do this is using synthetic division. So the polynomial is 1, 7, 11, and -3. Right, so we divide it by, let's try 1 to see if it works. Of course, we know it's not, but in real life, we have to test them if we don't know. Right. Right. So drop down 1. 1 times 1 is 1. 7. 1 is 8. 1 times 8. That gives us 19. 1 times 19. And that gives us 16. Now, previous section says that this is not equal. This is equal to the values of the function, but that's not equal to 0. So this is not a 0, meaning 1 doesn't work. Have to try something else. So we go to -1. Right, drop down to 1, -1, 7 minus 1 is 6, -1 times 6 is -6, 11 by 6 is 5, -5, so it gives us 8. And that is the values of the function at -1. That is not equal to 0 though. So that's still not a 0. And we're going to go for 3. And then -3. I mean, until we find one that works. Like I said, here we assume that we don't know that. 1, 7, 11, and -3. Right, drop down the numbers. 1, 3 times 1 is 3. That 7, 3 is 10. That 30, 41. 3 times 41 is 123. And that should be 120. Later on we say that if this is not equal to 0, then this is not a 0. Right? And then we have -3. right? Drop down to 1, negative 3, give us 4, negative 12, give us negative 1. Negative 3 times negative 1 is 3, and that is 0. So as you see, we use synthetic division a lot in this section. So this is equal to 0. So that check. That means negative 3 is a 0. So that's say we said. So negative 3 is a 0. And of course, and then we need the rest to be easy. Now, because if this is a 0, x minus negative 3 will be a factor. So in this polynomial, we can say x cubed plus 7x squared plus 11x minus 3 equal to, the factor will be x minus negative 3, so x plus 3, and the remaining will be, the other factor will be x squared plus 4x minus 1. Right? So now, the reason I do this because earlier we used a calculator, negative 3 equal to 0, right? So we know negative 3 is 0. Now, the synthetic division not only give us a confirmation that it is a 0, because remainder is equal to 0, so negative 3 is a solution to a polynomial equation, but also it gives us what is the other factor, right? So not only it shows that negative 3 is a 0, it also gives us what the other factor is. In this case, the rest of the problem, we can just let this equal to 0, which give us negative 3, and get this equal to 0. And this is a quadratic equation, so that should be easy. Negative b plus or minus b squared minus 4ac over 2a. Right, sorry, gotta run out of space here. Negative 4 plus or minus square root of b squared 4 squared minus 4ac over 2a. So we have negative 4 plus or minus 4 squared 16 plus 4 square root of 20 over 2. Right? Now, 20, if we break down 20, 2 times 10, 2 times 5 in the prime factoring, so 20 is equal to 4 times 5, or 5 times 2 square, if you will. Right? Then square root of 20 is equal to square root of 5, and square root of 2 square. Square root of 2 square is 2, so square of 20 is just 2 square root of 5. Notice, don't ever cancel the number like this. It will not work that way. That's why we have to write this is 2 square root of 5. And then we can factor out the 2. So we have negative 2 plus or minus square root of 5 over 2. Only then we can cancel out the 2. So our solution will be negative 2 plus or minus square root of 5. So our solution, of course, negative 3 is one of them. The other two is negative 2 plus or minus square root of 5. So there are 3 solutions there. All right. So the idea is the rational zero theorem gives us the possible solution. So if we have to guess, we only guess those solutions. Right. So one thing I can tell is 2 is not going to work. Yeah, only if it is rational number, it have to be in this form. So with that, we have those numbers, and then we just use integrated division to test them, right? Of course, if we don't know it, the calculator can help us. When we look at the graph, we see it go through definitely it go to -3. This is like close to -5, but we know it's not in the list, so it's not going to work. This is between 0 and 1. We don't have any rational number there. The only definitive one is -3, so that's what we have. Of course, we can see this one is -2 plus square root of 5, and this one is -2 minus square root of 5. Yeah, so those are irrational solution. Right, so that's what we have. Right, next, find the, wait. Right, sorry, let's pick this one. Right, so 4 zeros, right? Again, this probably take a lot of space, so we're just gonna cut the page in half. So first, we're going to find the possible rational zeros. So the factors of the constant divided by the factor of leading coefficient. So factor of -3 over factors of 2. Factor of -3 will be plus or minus 1, plus or minus 3, and factor of 2 plus or minus 1, plus or minus 2. Right. So we have 1 over 1, 3 over 1, 1 over 2, 3 over 2. 1 over 1, 3 over 1, 1 over 2, and 3 over 2. So those are the A0. Next, we check for the actual zero. So we're going to test for 1, then test for 3. The coefficient is 2, -1, -1, and -3. Right? We're going to test for 1 first and see if it works. On the text, this is a qubit polynomial. On the text, it's just 1. Because once we find a 0, we break down the problem to a quadratic equation. So only text is 1. If we can find the first 0, the rest will be easy. Right. So we'll try 1. Drop down to 2. 1 times 2 is 2. 2 and minus 1 give us 1. 1 times 1 is 1. that gives us 0, and 1 times 0 is 0, and negative 3. So 1 doesn't work. Not equal to 0. So this is not going to be a 0. Right? Try something else. Let's try 3. Two, negative 1, negative 1, and negative 3. Right? Drop down to 2. Give us 6. 6 minus 1 is 5. 3 times 5, 15. And that gives us 14. 3 times 14 is 42. And 42, that's 39. Right? Well, that's not going to be equal to 0 either. So 3 doesn't work. It might be a while until we go to actual the solution. But let's be smart here in this case. What we actually see here is, even though it's not equal to 0, so those are not 0. What we see here is one of them is negative and one of them is positive. And that is extremely helpful here. Remember, intermediate value theorem. We have 1, x equal to 1, and x equal to 3. When x equal to 1, the polynomial is negative 3. When x equal to 3, it is 39, it's positive. So the polynomial function, the graph is continuous. So we have to cut somewhere in between 1 and 3. So between 1 and 3 there is a 0. Right? So we're not going to test something else. It would be smart if we just find a number between 1 and 3 here, rather than just guessing the other solution. Because we know between 1 and 3 look like there is a solution. Alright. So in that case, between 1 and 3, well, 1 and 3. So look like the 3 half. 3 over 2 is 1 half is. So be smart here, and we just go to 3 halves. So the intermediate value theorem allow us to pick the more potential be a solution. Right, wrap out 2. 3 half times 2, 2 and 2 cancel out, so that's 3. Negative 1 times 3 is 2. 2 and 3 half cancel out. The 2 give us 3. And once again is 2. And that cancel out the 2 again, that's 3. And that's 0. Yep. And 0. And this is the values of the function at 3 half. Since it is equal to 0, this is equal to 0. So we have found the first 0. And not only that, it allows us to factor. So we say the function f of x is factored as x minus the 3 half, and then 2x squared plus 2x plus 2. If we solve this equal to 0, x minus 3 half equal to 0, give us the 3 half. So potentially we just need to work on the 2x squared plus 2x plus 2. All of that divisible by 2, so I'm just going ahead and divide by 2. If it's equal to 0, divide by 2 on both sides. X squared plus x plus 1. Right? I'll use quadratic formula here. Right. Negative 1 plus or minus 1 square b squared minus 4ac over 2a. So negative 1, we have 1 minus 4, so plus or minus square root of negative 3 over 2, right? Now, we have negative inside square root, that is imaginary, so this is negative 1 plus or minus imaginary I and square root of 3 divided by 2, right? So the solution is negative 1 plus or minus I square root of 3 over 2 and then 3/2. So those are the solution set. Now, if we have the calculator, it might help. We have 2x cubed minus x squared minus x minus 3. If we hit the graph, right, as you see, there's a solution between here, and look like on the list that is 3/2, right? 3 over 2, right? There's another way to do this too. We will find the intersection of the x-axis and then the graph itself. So go back to y equal 2 and y2 equal to 0. Now all we just need to find the intersection. So second, calculate, find the intersection. The first curve is this function. The second curve is this function. And when we guess, we just need to move closer to the solution. Hit enter. If we jump right into it, which is 1.5, which is 3/2. Of course, if we have a calculator, we can just do that to get 3/2. The imaginary solution, though, of course, did not show on the graph because the x-intercept only show the real zeros. Imaginary zeros will not show on the real number line, obviously. Right. So once again, all we need, if it is cubic equation, all we need is just one solution to get started. When we get one solution, the problem breaks down into just quadratic, and then we have the formula for quadratic equation, right? If we have a calculator, that would be nice to give us what the first zero is also, right? Now, if we don't have a calculator, we just have to guess, and the possible rational zeros, that's where we do use the rational zero theorem, give us the possible choice. And when we do this, if it happens to be one is positive and one is negative, just jump right in between and to get that is more potential to be a zero. In this case, it is. Right. We'll get back to more example on this, but now let's go to more theorem about fundamental theorem of algebra. So, fundamental theorem of algebra: if a polynomial has degree n, n greater than or equal to 1, then it has at least one complex root. So polynomial, if degree is bigger or equal to 1, always has a solution, always has at least one zero. Linear factorization theorem. So if it is a 0, then we can factor like this. If x equal to 3/2, then x by 3/2 is a factor. We talk about that. So for every 0, we can just factor in this form. The key here is, if it is degree n, then we have n factors like this. The factor may not be distinct, meaning we may have x minus 1, x minus 1, x minus 1, if it is multiplicity of 3. Right, next, the n degree polynomial has n0. So if in this case we have the third degree polynomial or cubic polynomial, we have 3 zeros. Again, it could count multiplicity. If we have 0, 1 is 0 multiplicity of 3, so that count is 3. So we may have x equal to 1, x equal to 1, x equal to 1 for qubit equation. So bottom line is the degree should be equal to the number of 0, and that including multiplicity. Right, next, if a plus bi is a 0, then the complex conjugate a minus bi is also a 0. Right, so we use the last part for this next example. Right, I'll find the third degree polynomial function with real coefficient satisfy this. Right, so now first we have 3 and I are 0, so let's say we have zeros, x equal to 3, x equal to I. Right, now if those are the zeros, then x minus those will be factors, so the factors will be x minus 3 and x minus I. Now what we have is if a plus bi is a 0, then a minus bi is a 0. For example, if we have the solution is negative 2 plus or minus 5i is a 0, but of course for real coefficient only. If it is a 0, then x equal to negative 2 minus 5i is also a 0. Right, so the real part will be the same. The imaginary, I'm sorry, if x plus 2i is a 0, then negative 2 minus 5i is also a 0. So the real part will be the same. The imaginary part, one positive and one negative. Right, so if it is real polynomial has real coefficient, if this is a 0, then we have another one like this. Now if I is a 0, then the one opposite to that, we just change the number from 1i to negative I. So according to this theorem, we also have x equal to negative I as well. And with that, we have the factor of x minus negative I or x plus I. Because those are the factor, we can say f of x equal to x minus 3, x minus I, and x plus I. Those are the factor. Now, we potentially might have a leading coefficient here. Doesn't matter what it is. If it's not equal to 0, then the 0 will be those numbers, these numbers. Right? That's exactly what this theorem is about. So we have the zeros, we can write out the factors, and here's the factor. Now the rest is simple. We will find a sub n by substitute 2 into this. But before doing that, I will just multiply this out to simplify things, if you will. Multiply this out. X times x, x squared, x times I and x, minus I and x, minus I squared. Always multiply the part that have the conjugates, the complex solution first, because they will cancel out. We should not have any imaginary here. And then I squared is equal to negative 1. So negative minus negative 1 is plus 1. So now f of x is just a sub n, x minus 3, and x squared plus 1. Right? and multiply this out. X cubed plus x minus 3x squared minus 3. Right? Of course, we can put them in increasing order of degrees. I mean decreasing order. Right. Now, it would be nice if we solve for a sub n, and one information we haven't used is f of 2 equal to 25. So when x equal to 2, I'm going to put 2 in here for x. Put 2 in for x. A sub n 2 cubed minus 3 times 2 square minus plus 2 minus 3. So put 2 in for x, and that will equal to 25. Right? So I usually like this, just say 2 store into x and evaluate this. Let's not do that. Do that first. So 2 is equal to x, and then x cubed minus 3x squared plus x minus 3. That is equal to minus 5. So we have a sub n times minus 5 equal to 25. We actually have space on the next page. Right, that's what we have. Right, and then divide by negative 5 on both sides. So it gives us negative 5. So f of x is equal to, now we can put negative 5 in here for a sub n. X cubed minus 3x squared plus x minus 3. Right. So we have f of x equal to negative 5x cubed plus 15x squared minus 5x plus 15. Right. So if we have zeros, we have the factors and the imaginary solutions, common pairs. Yeah. A plus bi, a minus bi, imaginary solution, common pairs, and that's what we have. And then multiply it out at the end, solve for the leading coefficient. What we have the leading coefficient, we have a polynomial. Right. This is another example here. Find the 4th degree polynomial. Right. Also, one thing I forgot on the previous example. This is the 3rd degree polynomial. So we will have 3 zeros, and so we have 3 factors, right? Because n degree polynomial has n zero, so we know that 3rd degree polynomial, they only have 3 zeros here, so there's only 3 factors, right? So this is the 4th degree, so there will be 4 zeros and 4 factors. So first, the 4 zeros. X equal to 2i. That's what given. X equal to 3 and x equal to negative 3. Right. Now, remember, if we have the polynomial with real coefficients, then imaginary solution common pairs, a plus bi and a minus bi. So the part that imaginary, we have to alternate the sign for that. So instead of 2i, negative 2i is also a 0. That's what we have. So those are the 4 zeros. Now if those are the zero, then the factors will be x minus 2i, x minus 3, x minus negative 3, and x minus negative 2i. So we can write f of x. Now let's put the real part together, x minus 3 and x plus 3, the real solution together, and the imaginary solution together, because when we multiply them out, always multiply the part that have the imaginary first. Right. And there will be a leading coefficient here, as long as it's not equal to 0. It does not affect the zeros for up front. Right. So I multiply it out. Right, multiply the imaginary parts, and then I multiply these two together, and then these two together. Multiply these two together, we have x squared plus 3x minus 3x minus 9. And now multiply the imaginary, the factor that have imaginary zeros, x squared plus 2ix minus 2ix minus 4i squared. Right. Good thing is, by the way, this always cancel because we only have real coefficient. Good thing is in this problem that cancel as well. And here I squared is equal to negative 1. So we have a sub n x squared plus minus 9, and then x squared minus 4 times negative 1, negative 1 times negative 4, so that's just plus 4. Right, here we can multiply it out, a sub n x to the 4th plus 4x squared minus 9x squared minus 36, and that gives us minus 5x squared. Right. Now we solve for the leading coefficient. So at x equal to 1, I'm going to put 1 in the polynomial. And that's supposed to be equal to negative 40. So we have a sub n 1 minus 5 minus 36 to minus 41 plus 1 is minus 40. So a sub n times negative 40, negative 40, negative 40 cancel out. So a sub n is equal to 1, and thus a sub n equal to 1. So the polynomial is just going to be this, x to the 4th minus 5x squared minus 36. So those theorems say that when we have the n degree polynomial, we're going to have n zeros, and with that we have, in this case, 4th degree polynomial, we have 4 zeros, and then there will be 4 factors, and then we just multiply it out potentially at the end. That gives us to solve for a sub n, and once we have that, we have the solution. Right. This is a relatively long section, so I'm going to stop here and then continue on the second part of this section. See you in the next video.